Hi, I'm Joy Adler,
And I'm Daniela Gill.
and we're going to be talking to you today about our research findings on the anorectic effects of neuropeptide AF associated with satiety-related hypothalamic nuclei. The neurophysiology of hunger and satiety in humans and other vertebrae has not been studied extensively. This is a difficult area to study as it integrates many different neuropeptides and regions of the brain acting on each other. In order to obtain a better understanding of the brain circuitry causing appetite, we must narrow down our focus to a single family of proteins.
The R85 peptide receptor family has a multi-ligand, multi-receptor system, making it susceptible to cross reactions. This makes it very difficult to determine exactly what substance is reacting upon what receptor to create the response you're observing.
Neuropeptide AF and the RF amides come from a gene that also encode NPFF, which has previously been proved to have many short-term anorectic effects on appetite in chicks. NPFF is localized in the human hypothalamus and was initially used to evoke pain sensitivity, but it has since then broadened its role in other functions. The RF amide peptide family has a strong therapeutic potential, as they have shown to play a role in energy, homeostasis, reproduction, pain reception, and behavioral processes such as food intake and stress response, which often go hand in hand.
Although NPFF has recently been proven to play a role in appetite suppression, the effects of NPAF have not really been researched. In this study, we attempt to isolate and observe the effects of NPAF on appetite in chicks with the hypothesis that it will cause a similar anorexic effect as NPFF. In order to observe the effects NPAF had on appetite, we ran an experiment that included a vehicle group with an ICV injection of 0 nanomoles used as a control, a group injected with 4 nanomoles, another with 8, and a third with 16. Each group fasted for 180 minutes prior to injection. The vehicle helped to observe if the stress from the injection alone influenced food intake.
Alright, now on to our results.
And experimentation.
In experiment 1, we measured the food intake, water intake, and blood glucose concentration. We found that the control and the 4 nanomole injected groups consumed similar amounts of food. The chicks that received 8 and 16 injections had similar levels of reduced food intake.
This leads us to believe that the threshold for anorexigenic effects is somewhere between 4 and 8 nanomoles. Reduced food intake could be correlated to 2 different response signals, either reduced appetite or increased satiety. We believe that since the dorsomedial, paraventricular, and ventromedial nuclei, which all play a role in satiety, showed signs of increased C-phosphominoreactivity levels, the reduced intake was possibly a result of increased satiety, despite the long fasting period before injection.
The intake for both food and water of chicks injected with 8 nanomoles shows a significant reduction from 60 minutes to the end of the observation. Chicks injected with 4 nanomoles showed a reduced water intake at 90 minutes and 120 minutes post-injection.
All doses caused reduced blood glucose concentration to a similar effect in comparison to the vehicle. This implies that NPAF might have an effect on glucose homeostasis regardless of what the chick's amount of food intake is. So in our second experiment, which was very similar to experiment 1, except for the fact that we withheld food to measure water intake, we wanted to take away the variable of hunger and solely observe the effects NPAF had on thirst. So water intake was reduced, but we had no significant findings at 30 minutes for any of the different groups.
It was, however, reduced at all other proteins in observation. At 60 to 120 minutes, chicks at 8 and 16 nanomole groups had more significantly reduced water intake compared to vehicles at 4 nanomole groups. At 150 to 180 minutes, all dosage groups had significantly reduced water intake.
So the second part of experiment 2 resulted in no significant effect on blood glucose levels at 180 minutes.
This shows that glucose levels are reduced in all groups injected, regardless of the amount being administered or food intake. These numbers are averages among the chick populations, which would explain why some values and their ranges are different from one to another.
So in experiment 3, we measured C-phosphominoreactivity in the PAPC, which stands for the parvocellular area of the paraventricular nucleus, and that had the highest neuronal activity. The magnocellular part of the PVN, called the PAMC, followed, but with a 40% drop in activity.
The DMN and the VMH followed with a 2% drop and a 6% drop. All of these nuclei are associated with NFAP and anorexia. Because these structures play a role in satiety, it could be possible that reduced intake was due to increased feeling of fullness rather than decrease in hunger. Experiment 4 measured quantitative behavioral effects, and here we observe 2 categories of behavior counted in time.
The term counted behaviors includes the number of feeding and exploratory pecks, jumping, distance traveled, and escape attempts. However, most of these actions did not result in a significant change after injection of NPAF, with the exception of fewer feeding pecks at 15 to 30 minutes post-injection, and fewer number of times jumped at 30 minutes.
The time behaviors were sitting, preening, perching, and deep rest. The results show the chicks spending more time in deep sleep at 20 minutes and less time spent perching at 20 to 25 minutes.
These results for this experiment are significant because it is the first report done on the role of NPAF on appetite in any species. The implications of the information gathered in this experiment have the potential to be largely beneficial to the public. Once more data is collected on this subject, it could be used in appetite suppression strategies to address the rising obesity rates and ultimately improve public health.
This experiment was very well done. Within each experiment, chicks from the same hatch were used, and from experiment to experiment, chicks from different hatches were used. This was in order to maintain consistency within the experiment, while also accumulating results of multiple experiments to show that the hatch was not a factor affecting food intake. However, the chicks with the hatch were randomly selected to receive a certain dose so as not to skew the results based on certain factors, such as sex or size.
Other measures were also taken to create a distribution of characteristics across groups throughout experiments to help emphasize the effects of NPAF over other factors.
One way this experiment could be improved would be by including another vehicle group that is not subjected to injection at all. This is because it could be considered a stressor to the chick, which may affect regular eating habits. We could then compare the feeding habits of the non-injected chick to that of the others.
Also, baseline measurements for intake and glucose levels in the chicks could have been included in the article.
For future experiments prompted by these findings to increase validity of results, we propose another possible experiment to observe more regions of the brain that play a role in appetite, such as hindbrain nuclei. It would also be interesting to see how chicks' feeding patterns would be affected if they were put under anesthesia while they were injected, to see if the stress from the injection plays a large role in the short-term food and water consumption.
You know, Julie, there's an interesting finding that another neuropeptide in the RFamides family, called prolactin-releasing peptide, or PRP, causes anorexia in rats, but was correlated to increased eating habits in chicks. So this might be caused by the divergence in the evolutionary tree that separated mammals and birds. And that could have resulted in the change of function of that peptide between the two species. So we could also, I'm thinking that we could do a future study looking further into the effects of PRP in both chicks and rats, individually and comparatively. So we will do this by injecting the subjects with varying doses of PRP and looking at the effects it has on appetite regulating regions.
Think you're onto something here. Additionally, due to behavior changes of the chicks, including less time perching and prolonged resting period post-injection, a further experiment could be run to observe the dopamine and serotonin levels associated with NPAF injections. Because the RF-amide family is known to cause changes in behavior, it is possible that less food consumption could be tied to a depressive state.
So these ideas are still in the works, so you won't see them quite yet, but given the incredible findings of this experiment, we're sure there's more to come soon.